So we've talked about some of the core concepts that we need in calculus. We talked about the big question, what's the slope of the line tangent to a curve at a given point? And that brought us to some other important pieces like what's a limit? What do we mean when we say the limit as x approaches c of f of x equals L? How do we think about it? How do we calculate those things? And that brings us to another important concept, which is continuity. So we want to think about continuity in the original idea from Newton, which was probably not his original idea, but he's the one that wrote about it first. Anytime in math something's named after someone, they probably most definitely did not come up with that idea. Like the Pythagorean theorem, definitely not Pythagoras's idea. That was like an old idea by the time Pythagoras slapped his name on it, or someone later on slapped Pythagoras's name on it. Do you know what I mean? So, like the scene I imagine, Pythagoras is sitting there and he's got a bunch of students, and it's like, oh, this is the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And the students are like, oh, wow, that's pretty dope. Did you come up with that? And he's like, oh, you've never heard of that? And the students are like, oh, no, we've never heard of that. It's like, oh, well, shit, yeah, I came up with that. That's called the Pythagorean theorem, named after me, Joe Pythagoras. And then that's how it became. And then people like later on showed up from like all around the world. And it's like, well, what's this Pythagorean theorem? And it's the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And they're like, oh, well, shit, we've known that for a long time. He's like, oh, yeah, but it's named after me, so I came up with it. I'm like, oh, shit. And then Thomas Edison was like, oh, yeah, that's how it should go. Anyway, what are we talking about? Oh, yeah, continuity. The original idea behind continuity was Newton trying to define things and being terrible at defining things. But he's like, oh, a function is continuous if I can draw its graph without lifting my pen off of the paper. That's his original idea. That's a great idea. Terrible as far as a rigorous mathematical idea. Great for an intuitive description. So our intuition around continuity is that we can draw the graph without lifting our pen from the paper. The idea is that we could just, like, all the points are connected. All the points are connected. There's actually a level higher than this called differentiability. This is what Newton didn't know about. Newton didn't have things like limits. That came later. First was the idea, and then there was the stuff that made it work. But our intuition is that we can draw the graph without lifting the pen from the paper. We need to be able to define this so that we can describe this in more rigorous terms, so we can really see what's going on. Most of the time, so we could really see what's going on in weirdo edge cases that don't matter much to the larger body of work as we move forward, but are important nonetheless mathematically. And last I checked, this is a math class, so that's what we're going to be on about. So we need a definition, and the definition involves limits. The fun thing is we're going to be defining continuity at a point. Does this all flow together? And we're going to do that by looking at one point. It seems ridiculous that we do it this way, but that's only because it's kind of ridiculous that we do it this way. It's like, well, how does this function flow together? Look at this individual point and see what's going on there. So we say that a function F is continuous at x equals c if and only if we're going to say three things in one thing. We're going to write one thing and imply the other two. A function f is continuous at c if and only if the limit as x approaches c of f of x is equal to f of c. This is our abbreviated version of a definition of continuity. It writes one thing, but says three things. The three things that are contained in this statement. Number one, the function is defined. I wrote f of c and I put an equal sign next to it. I am saying that f of c must be defined. So number one, f of c is defined. That is the first requirement for a function to be continuous at a point. Number two thing that I'm saying, at least implying, the limit as x approaches c of f of x exists. That's the second thing that's required for this third thing to be true. The third thing that we're saying in our definition is that these two values are the same. The limit is equal to the value of the function. So by writing this one statement, we're saying we're making three claims. A function f is continuous at x equals c if and only if, one, the function is defined at c. Two, the limit as x approaches c of f of x exists. And three, those two quantities are equal. The function is defined and the function is headed there. The if and only if part is a thing that we often use in definitions. If and only if is a double implication. It's a two-way implication. It says if A, then B, and if B, then A. That's an if and only if structure. If a function is continuous at x equals c, then this is true. The limit as x approaches c of f of x equals f of c. And if the limit as x approaches c of f of x equals f of c, then the function is continuous at x equals c. That's an if and only if statement. If A, then B, and if B, then A. This is different than just an if-then statement. If A, then B is weaker. If you get an A on the final, then I'll give you an A in the class. You can still get an A in the class without having an A on the final. And that does not negate that statement. Compare that to, you get an A in the class if and only if you get an A on the final. Now, those things are tied together. You cannot get an A in the class without an A on the final. I should use that one first because now everybody's stressed out. It's like, oh fuck, I have to get an A on the final? No, it's the first one. So I've used this if and only if a couple of times. I want to make sure that we all understand that's an if A, then B, and if B, then A. And the and right there is a logical and. It means both of those things. So this is best, the best thing to do here is give examples where this is not true. Because a continuous function just means we can draw the graph without lifting our pen from the paper. So if we have to lift our pen from the paper to draw the graph, that means one of these three things must be broken. So let's draw a graph where these things break in various ways. Let's say we have a graph. So here are two places where the graph does not have a value. So there's that little hole in the graph, and then we've got this vertical asymptote, similar to what we had yesterday. So our function is discontinuous at x1 because the function is not defined at x1. The function is discontinuous at x2 because the function is not defined at x2. Also, the limit does not exist at x2. That's two strikes against x2. The function is not defined and the limit does not exist. So the third one can't even be brought into question because the function is undefined. There's nowhere to say equals undefined. In x1, the function is not defined, the limit exists. F at x1 is undefined. F at x2 is undefined. At least at x1, the limit exists. So we can say limit as x approaches x1 of f of x exists. But the limit as x approaches x2 of f of x does not exist. And the function is going to do some more stuff. Here at x3, the function is defined, but the limit doesn't exist because the function is not headed towards one value. That's the color scheme. I don't know why I'm so dedicated to the color scheme. So at x3, we see that the function is defined. But the limit as x approaches x3 does not exist. It doesn't exist for a different reason than at x2. At x2, the limit doesn't exist because the function is going off towards negative infinity. Here at x3, the limit doesn't exist because the limit from the left is one value and the limit from the right is another value. So here, our limit is undefined for different reasons. Limit as x approaches x3 from the left of the function is not equal to the limit as x approaches x3 from the right of the function. Any questions? I'll start, okay? So then the function continues on. Put this one down here. Here at x4, it's the third piece that's not working. We see that the function is defined, f of f4 is defined, and the limit exists, but those two are not the same value. So the function is discontinuous. So up here, we see that f of x4 is defined. Down here, we see the limit as x approaches x4 of the function exists. I don't know why I'm shouting. Calm down, dude. I don't want to try to imbue this with fake enthusiasm. The problem here at x4, we can see that the function is discontinuous. It breaks our intuition. To draw this function, I have to stop here, jump up here, draw a point, and then come back down, and then continue on. So the problem here is that the limit is not equal to the value of the function. The limit as x approaches x4 of the function, which exists, is not equal to the value of the function, f at x4, which is defined. So we see that f is discontinuous at these 4 points. Everywhere else, f is continuous. F is discontinuous at just those 4 points. F is continuous everywhere else. If we pick any other point, oh, F is continuous. If we pick any other point, like here, we see that the function is defined. There's a point there. and that the limit is the same as the value of the function. We look at what the limit is headed to, it is pointed right at the function. Continuity is just about the function being connected. We're looking specifically for places where the function is disconnected. Any questions? 3 requirements. The function is defined, the limit exists, and those 2 values are the same. One of the things we have to remember is that infinity is not a value. And number 2 thing that we have to remember is that this statement, we can draw the graph without lifting pen from paper. That's an intuition statement about things. So it doesn't count that I technically, oh, just draw the circle and then just keep going. I mean, you know what I mean. You know what I mean? It's our intuition. We're just trying to get an idea about how to describe it. And that circle there is actually not part of the graph. That's just calling your attention to a hole that's in the graph. This is why when we graph stuff on Desmos, it doesn't, unless we zoomed in really far, we can't actually see the gaps because it doesn't label them. It just says, fine, you can't lift, you gotta lift your pen from the paper. So it just stops and then starts. So like 1 pixel is left blank and then we can't see it because our eyes don't have the same resolution as a computer screen. Any questions? It's infinitely better because our eyes are like continuous. The screen is discontinuous, or not discontinuous. The screen is discrete. Any questions? How's everybody? Yes. So if you want to see if there's a function that has like a hole in it, then we would, one way to get that is to have like a factor that cancels out on the top and the bottom. So a graph that has a hole could be a function, my f of x equals x squared minus 4 over x minus 2. F of 2 is undefined. There, we cannot put a dot anywhere where x equals 2. But we can't, if we look at the graph, we can simplify this. The graph looks like x plus 2. So it looks like that line, except for one value. Because this function is not equal to x plus 2 everywhere. Specifically, it's not equal, they're not equal when x is 2. So we're going to draw the line x plus 2, except there's going to be a hole in the graph at 2. So when we have a factor that cancels out in the numerator and denominator, that produces a hole in the graph. Unless it produces an entire asymptote. I don't know why I'm trying to draw such a tiny little graph. But I'm just going to draw the line x plus 2. But when I get to 2, there's a hole in the graph, and then it keeps going. We draw a big ass circle where there's a hole in the graph to indicate that there's a hole there when we're drawing things. We can't just leave an empty space because it'd be hard to see. questions? Factors in the denominator that can be zero either produce a hole in the graph like this, or they'll produce a vertical asymptote. Those are the two things that can happen. So zero denominators can also produce vertical asymptotes. So if we think about flipping this, I don't know why I want to flip this over so much, but if we flip this over, the x minus 2 cancels out. Oh, now I remember why. So we can cancel out the x minus 2 again. But these two expressions are not the same. This expression is undefined for plus and minus 2. This second expression is only undefined for negative 2. So these things are only equal so long as x is not 2. Even though it's clearly undefined for negative 2, these two expressions are not equal when x is negative 2, because this expression has no value. So we can go ahead and have a pedantic argument in the comments, except for the fact that I turn comments off. It's not important. What is important is that the one that cancels out, that's going to produce a hole in the graph. The other one that's left behind is going to produce an asymptote. So we have a hole in the graph. And then we have a vertical asymptote at negative 2. These are just some things that could happen in rational functions, cause functions to be undefined. It may be that you didn't talk about these graphs of rational functions in high school, which is reasonable because you can't be in front of a high school class and be like, oh, graph holes and asymptotes. As high school students would just like start snickering. At a certain point, I did realize that I was the whole problem in there, because I was like, graph hole, asymptote. And then I point out when mathematicians cut each other off in traffic, that's what we yell at each other. Graph hole, asymptote. I'm just kidding. Just like everybody else, we just say fuck you. Then it's dueling integrals at 10 paces. I'm just kidding. Although you should note that if you do challenge me to a duel, as the challenged person, I get to choose the weapon, and I will always choose integrals. So you're like, oh, pistols or swords? Like, oh, no, it's my choice. Integrals. Integrals at dawn. No calculators. No phones. Just whiteboard and pen. And I'm like, oh, what? You start off. I'll start off. I give you an integral. If you can find the antiderivative of the function that I give you, then you can give me one. If not, then you lose. Kind of at the end of this class. Actually, halfway through this class, because I don't know, do things weird. We know how to do derivatives. We know that first shortcut to derivatives. Just do that backwards. That's an antiderivative. That's why we came up with the clever title, antiderivative. It's like, I'll do that backwards. So instead of multiplying by the exponents, then subtracting 1 from the exponent, just invert that process. Add 1 to the exponent, then divide by the new exponent. Congratulations, you just did some stuff from chapter 6. But yeah. You mean we just skipped 3 chapters? Yeah, because it's week 3 and we've already done some stuff from chapter 3. How's everybody okay? It's because I know y'all can handle it. Our biggest problem right now with the whole shortcut thing is talking to Canvas. That is an indication that we can totally handle finding derivatives. So what we would have here is we have a hole in the graph at 2 and then a vertical asymptote at -2. Now this graph 1 over x plus 2 is just going to look like our typical hyperbola. I say this is the typical hyperbola and not the x squared minus y squared one. I like for this one. Vertical asymptote at -2. And then we'll just draw a hole in the graph at 2. Graph holes and asymptotes. One of the graphs had, one of the points of discontinuity, we had the graph with a hole in it and the limit exists, but then the function was defined somewhere else. For that, we typically have a piecewise defined function. So if we have a piecewise defined function, that's where we might see things like holes, not just this kind of hole, but holes and jumps. So for example, if p of x looks like the function x plus 2, if x is less than or equal to 0, and x squared if x is strictly greater than 0. This is a piecewise defined function because we're defining it in pieces. We use different functions depending on the input. So what we'll see is the line x plus 2 for the non-positive x's, and then for the positive x's, we'll just draw the parabola. And this will have a jump. We'll jump from the point 0, 2, the y-intercept of the line, and the vertex of the parabola. So here, before 0, we're going to see the line x plus 2. And then after 0, we're going to see the parabola, x squared. Usually when we're drawing by hand a function with a jump discontinuity in it, we make sure that we indicate where the function is defined with a heavy dot, and then a big giant open circle where the function is not defined. Another thing that can happen in a piecewise defined function is that we can have here, I took what's going on at 0 and I just attached it to what was going on previously. We could separate out in a piecewise defined function. we could say it's going to be x plus 2 if x is strictly less than 0, and x squared if x is strictly greater than 0. And then I can indicate what's going on at 0. Right now, the function is undefined at 0. But I could just give it a value. 5 if x equals 0. So here's the line, x plus 2. Here's the parabola, x squared. But what's actually going on at 0, the function is equal to 5. Any questions? I usually take this diversion because we don't always encounter piecewise defined functions at this point in our mathematical career. That's everybody okay? Everybody looks so stoked. It was like, oh, we've seen piecewise defined functions. We totally have all seen this before. But we're going to pretend that we haven't. It's like, oh no, I get it. And then you can pretend like you pick things up really fast. It's like if nobody recognized Shaquille O'Neal and you like walked onto a basketball court. So, hey, what's this game you guys are playing? And I'm like, oh, it's called basketball. You've never heard of this? Like, oh no, can I give it a try? And they're like, oh wow, you're really good at this. I'm like, oh wow, I've never done it before. This is my first day. And I was like, oh whoa. You know what I mean? Or there's the other one. This is called Leach's gazelle theory. It's like, I'm not called piecewise defined function. And in your mind, you're sitting there going, what the F is a piecewise defined function? I'm like, well, here's an example of a piecewise defined function. You're thinking, holy shit, I've never seen that before. But you're not going to look like you've never seen that before. You're not going to look like, oh, what the hell is this, Leach? I've never seen this before. Because you're worried that that'll show like some kind of weakness. And then it's like, oh, I've never seen this before. Then I'm like, oh, that's unfortunate. And I'm like, pull a lever, and like a lion drops out of the ceiling, identifies you as the weak gazelle, and then eats you. And I go, well, is there anybody else who's never seen piecewise defined functions before? And it was like, oh, no, because you've all jumped up and run away because the lion had already eaten the gazelle. See what I mean? So now I don't blame you if that's your mindset, because that's kind of the trauma that we inflict on you as math teachers. A lot of times we are dicks about it. It's like, well, what do you mean you don't know this stuff? And your response as a student, at least in your mind, should be like, oh, motherfucker, that's why I fucking hired you, so I could find this stuff out. Like, don't blame things don't blame people for not knowing things that you should have been taught them in the first place. You know what I mean? It's like when old people are like, oh, kids today can't even write cursive. Motherfucker, you didn't teach them to write cursive. How do you expect to know it? You think you could come with that? Were you just born with fucking cursive? And second of all, no one can fucking read it anyway. Let's type some stuff. Oh, I can't type stuff. No. Fuck you, old people. You know what I mean? Oh, kids these days can't change a tire. Blah, blah, blah. But for the most part, we don't have to. Update your car, Grandpa. Get some fucking run flats. And learn how to text. An actual modern thing. Do you know what I mean? It's not cool to make fun of people for things that you didn't teach them. Like when you were born, I don't know if I mentioned this, but when you were born, you came preloaded with exactly one app. Like if you open up the baby interface, there's one app on there. It's like, oh, if uncomfortable, make noise. That's it. That's the one thing that you know how to do when you're a baby. So I go hungry, wham. Sleepy, wham. In pain, wham. It's one app. You don't even have the fucking sleep app, right? You can't even like select sleep. And parents are like, oh, go to sleep. And the kid's like, oh, I don't know how, fuckers. You have to teach me that skill. You know what I mean? You got one thing that you can do. Uncomfortable, make noise. That's it. That's all you got. Everything else is learn. And so if you don't know something, that's our fault. Don't ever take shit from someone that says, oh, why did you not know that? Be like, oh, fucker, you didn't know it either. You know what I mean? I find this especially galling from teachers. My new thing is like, oh, say the obvious thing. Because it might only be obvious to me. You know what I mean? Never be worried about like, I don't know what this sign function is. I'm like, oh, holy shit, that's okay. You know what I mean? Fuck. Teachers piss me off. Parents piss me off too. That's a whole separate thing. All right. So this is one of the things that we need limits for. It gives us another, it just gives us, it's another way for us to think about limits. The idea is a continuity. We can draw a graph without lifting our pen from the paper. The function is connected. The function is connected. That's what we want. The function is connected. All the points are connected to each other. How do we define what we mean when we say that the function is not connected? There's a point where the function is discontinuous. There's a point where we have to lift our pen from the paper. These points are not connected to these points because of this hole in the graph. Any questions? There's a higher level of this. Tomorrow is continuity too, which is going to be differentiability. Are the points smoothly connected together? Smoothly connected together. This function is discontinuous at x3. The function is defined because I filled in that hole right there. But the limit doesn't exist because we're headed towards one value from the right and a completely separate value from the left. So we're not headed towards one value. I can't say that the function is within epsilon of anything. Because if I put an epsilon around here, then coming from this side, I'm within delta of x3, but I'm nowhere near this value. Any other questions? Is that okay? Fine. That's it. I was grumpy at your previous math teachers. Send me their names and I'll grump directly at them. I'm just kidding. Don't send me their names. I shouldn't know these things. That's it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing.